So this is part review. So way back in Calc 1, we looked at Pascal's triangle here. And Pascal's triangle is a shortcut to get the coefficients of a binomial. So for example, like 1 plus x to the 4th power. The coefficients for that are going to be 1, 4, 6, 4, and 1, which are this row of Pascal's triangle. Now, Pascal's triangle can be found by just taking the two numbers above and adding them to get the next number below. So we could generate the 5th row of Pascal's triangle by just adding the pairs of numbers above. There's always a 1 on each end. Now, it turns out those numbers are also what are called combinations in mathematics. And a combination is a collection, it's a calculation based on factorials. So again, for a power r and column n over here, it's r factorial over n factorial times r minus n factorial. And that's what I have written out down here. So for example, this one right here, r is 4 and n is 3. And so this calculation right there leads to those numbers, and those numbers clean up to be 4 here. Now, and if you clean up those factorials, the r minus n factorial on the bottom cancels out a whole bunch of the r factorial on the top. So you end up finishing at r minus n plus 1, wherever that is. So if you look back up to the green one here, that means the first version of this right here for r equals r and n equals 0, you get a coefficient of 1. The next version of this right here would be r. The next version of this right here for n equals 2 would be r times r minus 1 over 2 factorial. Then r times r minus 1 times r minus 2 over 3 factorial. Guess what the next one's going to be? It's going to be r times r minus 1 times r minus 2 times r minus 3 over 4 factorial. And you just keep going until you're done. The binomial theorem is, again, this for whole numbers. And if they're whole numbers, it's eventually going to zero out and stop giving you coefficients. It just ends. The weird thing is, though, for the yellow highlighted version of this factorial formula, if r is not a whole number, these keep going forever. And you end up with an infinite series. So, for example, for r equals power 1/2, I'm applying this formula right here. So the first coefficient is going to be a 1 from that. The next one's going to be a 1/2. The next one's going to be 1/2, so r times r minus 1 over 2 times 1. That simplifies to negative 1/8. Next one would be r times r minus 1 times r minus 2 over 3 factorial. That simplifies to 1/16. And again, I can keep generating, based on this formula right here, new coefficients. And this keeps going and going and going. Now, this is an alternative to, how would we do this otherwise? How would we find the series for 1 plus x to the power 1/2? Well, we'd use Taylor's theorem by taking repeated derivatives. So it turns out if you do take repeated derivatives of this and divide by n factorial each time, it'll lead to exactly these numbers right here. So this is an alternative to Taylor's method to get the coefficients if you have something like 1 plus x to a power. Now, it doesn't have to be 1 plus x. It could be 5 plus x squared. It could be x plus y. It works no matter what two things you're adding here and no matter what power you have here. And again, the bottom line is, based on this formula right here, if r is a whole number, it ends up zeroing out when r and n match, after they match. And if n is not a whole, or if r is not a whole number, the terms just keep going and going and going. We end up with this infinite series. And these are always the coefficients of that infinite series. So this is the extended binomial theorem. And the first third of this section right here is, given some binomial raised to a power, we're going to use those to generate the coefficients. So your job is to get used to using that formula right there. And that is my cue. I get to go play with 8th graders next. So what I'd like you to do here is just try on paper writing out the coefficients for 1 plus x to the 1/2 power. See if it leads to the coefficients I have here. Try it for 1 plus x to the negative 1, and then jump into the homework. And the first 5 problems in the homework are just like this. Okay, so give that a shot.